Hello there. This is week 2 for the R component of ACTL1101. Today we talk about data structures, importation, and exportation. It's a relatively big week, so let's jump right in. Learning outcomes. Run R and RStudio on your own computer. Understand how to use R and RStudio. Recognize and create different data structures. We'll explain along the way what we mean by a data structure. Demonstrate the advantages of different data structures, extract information from different data structures, perform mathematical and set operations. Then lastly, import external data. So we want to bring some data into R to analyze it. But then also if we've done some manipulation, sometimes we want to export data into a folder that we can then use for other purposes. Now, just a few words about R and RStudio. Now, in the previous lecture, we could rely solely on the Ed platform to run our R codes. I think now is a good time for you to actually install R on your computer and RStudio as well. I told you you don't need to install anything last time. This way we can kind of ease our way into R programming. But of course, in real life, when you program, well, you will program not out of Ed, but out of your computer on which you need to install whatever programs you use. And potentially in your future job, you're going to use RStudio. And then in the more short term, for the main assignment of the course, you will need to have installed R and RStudio on your computer. Now, just a comment that why do we have those two things, R and RStudio? So R is the main software. You could also say R is a specific programming language. Obviously, there's others like Python. So it's the software. Now, RStudio is what is called an integrated development environment, which in essence makes using R way more convenient, sort of user-friendly. So because of that, most people use RStudio when they program in R. So now there's detailed instructions here. I can open them, but I'm not going to go through them because it's very straightforward. It's like downloading any program basically. You can follow the instructions there, but you have a few links to click. And then usually you go there and okay, English, okay, and then next, and etc. Eventually you'll get to the bottom and you'll have R on your computer. Shouldn't take too long. Now here on this page, you have specific instructions for Windows and slightly different instructions for Mac. But again, I'll let you go over this. If you have trouble with this, send us a message on the discussion board. So now just going back to my slides. Okay, and if you use Linux, well, if you use Linux, you're probably a computer science person, so I'm sure you're gonna be able to work it out for yourself how to install it. Now as well, here I'm gonna do a brief demo of RStudio, but I do strongly recommend that you watch this video. So on the slides you can actually click here. Maybe it's gonna open it for me as well. Yeah, it goes here. So in essence here, this is a short video that's going to take you through all the steps, not the steps, but the general environment of RStudio. And as one of the YouTube user put it, this video of yours is better than 4 2-hour lectures from my professor trying to explain how RStudio works to us. And again, this is the video you can access by clicking this. It's not my video at all. It's just found on YouTube. But now I don't want to be accused of not doing my job. So let me just briefly open RStudio myself and show you a few things there. So if we go here, RStudio, and by the way, you should have by now installed RStudio. So hopefully you see something similar to this. So a few things here. Now for me, I only see the console. The console for now is where, well, your code is actually executed and you can see the results. So as we've done on Ed before, if I type something like, I don't know, just a mathematical calculation, maybe whatever, pi to the power of 5. Okay, I get the result. But now here there's also this source thing that I can open, or maybe I want both, so I'm going to do something like this. This is, you see, an untitled file. So in this source, this is where I would actually write my R code that I can then save. Exactly like you would save maybe a Word document or any other sort of document. to preserve your code, to save it and then reuse it later, you would type your commands here. So for example, I can remember that the hashtag means a comment. So here I could type a header, something like my first R script. Okay, and that's very exciting, of course. And then, I don't know, something else, maybe author. This is me, Gilly. And then, I don't know, the date. Okay, just to make it neat. What date is it today? 7th of June. And then I would then start with my first code. So again, I could type a R command that then I want to execute. So maybe I'm going to try to generate some random uniforms, for example. I want to generate 10 of them between, well, the default is 0, 1, but maybe we want to default 5 to 10. And now, then I can run my code, clicking this button run. And if I run it, the results will appear here on in the console. Okay, so the first part is just a comment, doesn't do anything, but then RUnif is of course going to generate my 10 random uniforms. And again, the point is that I can save this file. So I would click here, save document, and then I can save it somewhere on my computer so I can then reuse it later. So here, I mean, I don't think I'm going to reuse this file, but let's say that I just save it to my documents. I call it, I don't know what to call it. Again, my first R script. And then you see it's going to have an extension .r, which is a specific type of document. Okay. And now I have my document saved. This code, I can then exit RStudio. Let me just show you this. Yeah, just click exit RStudio, but then I can open RStudio again and find my document by loading it like I would do if I open a Word document or any sort of document. I'm just waiting for RStudio to open again. I don't know why it's taking a moment. Okay. And now actually, you see it's already there. Just R has some memory of what files I was using recently. But let's say that I just close it. I can go to File, open File, and then I should be able to find my my document here. I had saved it in my documents. So I open it, and I can run again this command. And then keep going. So if you have a medium size or big project, you're going to save your R script somewhere, and then you can work on it later when you go back to it. Okay, pretty straightforward. Now, just a word. There's other things here. I think for now, I'm not gonna spend too much time on this, but this environment is where you can see all the objects you've already created in R. So for example, if I put those 10 random numbers in an object that I call my vector, for example, now this for now doesn't do anything because I haven't run this. But if I run it, now I will have created a vector that contains all those numbers. Now notice they're not displayed because all this command does is create the vector that now contains it. I haven't displayed the result, but if here after I've created the vector, I want to actually display it as we've done last week. Now if I run my vector, well, just to show you that my vector already exists because I run my vector first. Or already, if I put a comment here and then I run only my vector, well, I actually see the results because my vector exists. And you see in this environment panel, it tells me, okay, my vector is a numerical vector with 10 elements, 1 to 10. And again, if you directly type my vector in the console, it will also work. And you see actually, as I type it, R tells you, okay, there's an object called my vector here. You can click on and then enter. I get my results. And of course, if I type some other commands, maybe I want to put my vector to the power of 2, then obviously it's gonna work. Okay, so that's the environment. It reminds me, or it tells me what objects are currently exist in my session of R that I can use. And okay, here files, I can navigate my files to find a specific document. Plots, this is where any graphical plots or other graphical things would be displayed if I create some. So let me just show you. If I type histogram in the console here of my vector, it should create a plot. Yes, and I see here, okay, it's not too meaningful because I only have 10 observations, but you see what I mean. The plots will be displayed here. Packages, I'm gonna probably talk about this later. Help is where you can search for a specific R function. So maybe I don't know what RUnif does actually. So if I type RUnif here, it should find it and then give me information about it. The general description, the syntax to use, the arguments of the specific function, and some more details. And then usually at the bottom there you have some examples that could actually be the most useful part. Okay, so in a nutshell, help here can be quite useful to find information about specific R commands or functions. Okay, for now, I think that's enough for RStudio. But remember, this part is where you type your code that you want to save, and in the console, the code is actually it's actually implemented. But those commands, if I close R, I'm going to lose whatever I've typed here if it's not in my saved R script. Okay, enough of RStudio. Now let's jump back in the slides to cover some content, because as I said, we have quite a few slides to cover today. As a general comment, I think this week, again, we learn, I don't want to say basic things, but we learn R structures. So data structures, how R is saving or well, structuring pieces of information. So it's going to be maybe a little bit dull because we need to cover quite a few different types of data structures. We're not yet going to do like interesting things like statistical analysis or visualization, but this is coming later. But we do need the basics before we get there. So again, my apologies if this lecture is slightly boring. Hopefully we do slightly more interesting things later. But now, the first data structure is the vector. And we've already covered vector a little bit last week. It really is the fundamental data structure in R. Now, what is a vector? It really is just a sequence of data points of the same type. So all numerical, or maybe all characters, or all logical, but within one vector, the data types are the same. So for example, my vector here, it's creating a numerical vector, again, using this function C of those specific numbers. We saw that mathematical operations are performed on a vector element by element. So my vector times 3, every single element of the vector is going to be multiplied by 3. Now, to recover specific items of the vector, we need to use the squared bracket notation. So my vector here, square bracket 1, means I'm going to grab the first element of that vector, which in this case is, of course, 7. My vector square bracket 3, 13. Important that it's a square bracket. If it's a regular bracket, it's not going to work. Okay, now we look at some operations we can perform on vectors. And those are functions in R that you can feed to those functions a vector. In those examples, I think it's all numerical vectors. And then the function will return something specific. So length simply tells you how many elements are in the vector. Sort will arrange the values in ascending order. Reverse will just rearrange the elements in the opposite order. Rank returns the vector of ranks of the elements. By rank, we simply mean that the smallest will have a rank of 1, the second smallest will have a rank of 2, and so on. The largest will have, if there's 10 elements, the largest will have a rank of 10, and so on. Head just gives you the first few elements of a vector. Let's say that you have a huge vector and you just want to see the first few. Sometimes that's useful. So you use head and tail, same thing, but you'll get the last few elements of the vector. Let's see all those functions in practice. So here I'm declaring x to be my vector, again using this assignment character. So it's a vector with all those numbers. Now note that some of them are repeated. So 1 is there twice and 8 is there twice. That's going to be important in a moment. So length, there's 10 numbers in this vector. If you count, yes, you count to 10. Sort, okay, they're sorted in ascending order. Sort, as a second argument, you can put decreasing equals true. Now, decreasing is false by default. So if you don't put it, you're going to get ascending numbers. If you put decreasing equals true, obviously you're going to get the same thing in the reverse order. So starting with the largest value, finishing at the smallest. Reverse, it just totally flips the elements of the vectors, right? So this vector, the first element 8 becomes the first, and the second last becomes the second first, and so on. The last one is 1. Well, 1 is here. I think you see what I mean by reverse. Rank, as I said, gives you the rank, but there's a bit of a catch. Here you get 0.5s. Why is that? Well, The smallest value in this vector is clearly 0. So 0 will get a rank of 1, exactly, because it's the smallest, so it gets a rank of 1. However, the second smallest is 1, but 1 is replicated twice, so the rank of both the first element here and the third last here, they both get a rank of 2.5. What's the logic of that? Well, if this was the second smallest and it was unique, it would of course get a rank of 2. And this, if this was the third smallest uniquely, it would get a rank of 3. So because of that, those two get the average rank. So the average rank of 2 and 3 is of course 2.5. Okay, and the same logic applies to the biggest one. So 8 is the biggest, the largest number there, but of course ex equal with the other 8. So instead of getting ranks of 9 and 10, they get the average rank, 9.5. Okay, head, I think by default, head gives you 5 elements, 5 or 6. But then if you say head x3, you're simply saying, okay, what are the 3 first element of the vector? Obviously 1, 3, 6, and here tail, the same thing. What are the last 2, in this example, elements of x? Okay, note here, the largest value of rank x is not always equal to length x. Well, yes, just because there can be ties for the largest values. Okay, so you can perform what is called here set operations on vectors. So I think it's easier to review this with the example already. So imagine A is a collection of those numbers, also known as a vector, and B is the collection of those 3 numbers. Intersect AB. So again, intersect is a specific function that returns something. It gives you the elements that are in common between A and B. So of course here, 2 and 7 are in both vectors. So intersect gives you 2, 7. Union, you guessed it, gives you all the elements that are in A or B. So basically it gives you all the elements of both vectors, but without duplicates here. So 7 is in both, 2 is in both, but they're displayed only once here. Set difference AB. So set difference AB, and the order here matters. So it means elements that are in A, but not in B. Okay, in A, but not in B. So we can see here 4 and 5 are in A, but both 4 and 5 are not in B. While 2 and 7 they are also in B, so they are not displayed here. So elements in A and B. But careful that this is different than set difference BA, because again, this would be elements that are in B, but not in A. But if you look at B, only one is unique to B and not also featured in A. So you get only the value 1. Okay, is element AB. So now this is a bit different. It returns a true false. For every element in A, it checks, okay, is it in B as well? And then it returns a list of true false. So the logic is here is A has 4 elements, 4, 5, 2, 7. And so 4 is not in B, so that's a false. 5 is not in B, so that's a false. 2 is in B, true. And 7 is in B, true. But again, the order here, of course, matters because is element BA would be answering true false, also a true false question, but a different one. So it's basically answering each element of B. Is it in A? Well, let's see. B2, is it in A? Yes, so true. Then the second element of B is 1. It's not in A, so it's false. And the last one, 7, is of course in A, so we get a true. Now, is element is actually used often enough that apparently R as a shortcut for it. So in essence, maybe you need to use is element written like that because you have the shortcut $ in $, which perform the same thing. So, and maybe it's actually easier to read, right? Because it's basically asking the question, is this in this? And gives you the answer. Now, 4 is just a number, so it's a single numerical value. So is 4 in A true? 4 is there. But then is A in B? Now that's an element by element comparison if there's many elements in A, such as in this case. So A and B perform exactly the same thing as is element AB. Okay, it's a shortcut. Okay, I think that's enough for this specific slide. So exercise for you. Maybe take a second to figure it out. So given again some vectors here, A, B, C, calculate the collection of elements of A and B that only belong to one set. So elements that only belong to either A or B. Take a second. This one is maybe not so obvious. Okay, I'll give you the solution. So elements that are only in A and not B, that's set difference AB. And elements that are in B but not A, it's set difference BA. But now you want all of those, those that are basically unique to one of those two sets. So you can take the union of that, right? So I think we already had set difference AB in the previous slides. They're slightly different, those things. So it's not exactly the same. I mean, 4, 5 is, but then B, we've added a character to it. But I think you see what I mean. You just join, so you take the union of those two, those two set differences. And then the number of elements that belong to A and B and C. Now, this one as well, you need to think about it a little bit. How can you do this? Well, it would be intersect, but there's a bit of a catch. I mean, I trust you have paused the video now and you're in RStudio trying to figure it out. So as for myself, I'll just present the solution. So, I mean, there's two catches. The first one is that you want the number of elements, right? So you don't want the list of elements. You want to know how many there are. So you need to use length of a specific vector. But this vector is obtained, in essence, you need to intersect embedded in another intersect. So the inner one is the elements that are common to A and B. But then those ones, you can then look, okay, are they also in C? And that will give you the intersection of ABC. So intersect those elements that are in A and B. And again, intersect again with this result with C. And that gives you the global intersection. And so again, this would give you all the elements that are common to ABC. Here we can easily see that it's 2, 7, 2, 7. So yeah, so it's 2 and 7, but then the length of that is 2. And I'm pretty sure that you need this, like intersect, I'm pretty sure it doesn't accept more than 2 elements. Let me just double check in real time, but if I remember correctly, let's say that I type here this, and I'm guessing that intersect A, B, and C is not gonna work. So let's try. By the way, if you don't want to execute the whole script, so if I click run, it's gonna execute everything. Is it? Actually, I'm a bit surprised, but yeah, okay, that doesn't work. Yeah, intersect A, B, C doesn't work. Now I'm a bit surprised if I click run, it doesn't run everything. Okay, that's quite interesting. But anyway, what I wanted to say is if you select something like this with my mouse, I'm selecting only those commands. With the shortcut Control Enter, it's gonna run exactly only the selection. So in this case, it would run this, but I already know it's an error. Okay, again, what I need to do is, well, intersect again. Interrect, no, that's intersect. Okay, now I get my 2 and my 7, but I already knew that. Now, what's often quite important to be able to do is extract specific elements from a vector. Now, we've already seen one way to do that, which is using the square brackets. But now we just give a bit more information about that. So what we said is that my vector and then I, but I is for whatever number, will give you the ith element in the vector. But there's more ways you can use that. So in essence, I doesn't need to be a single number. It can be a series of numbers. So for example, here I declare a new vector with those 5 numbers, 2, 5, 6, 8, 10. Now, vec, then square bracket, another vector. What does it do? It extracts the items or the numbers in this vector, but that have positions as specified here, in this case 2, 3, and 4. So I'm picking the second element of this vector, the third element, and the fourth. So of course, the result will be 5, 6, 8. Again, those are the numbers or the indices of the elements of this vector, second, third, and fourth. Okay, this is just a more compact notation to do this. So vector, and again, square bracket 2 dot dot 4. But you know that 2 colon 4 is actually the series of numbers 2, 3, 4. So I get the same result, 2, 3, 4. Now, you can use this to exclude specific values. By exclude, I mean vec minus 3 means every element except the third, right? So every element of the vector except the third. Again, the third here is the value 6, so I get all the others, 2, 5, not 6, and then 8, 10. And you can have fun. You can have several indices that are negative, so several elements to exclude from the vector. In this case, if I exclude the first and the last, well, the last being the fifth here, I will get yet again 5, 6, 8. Okay, next way to extract elements from vectors is what is called logical masks. So this works by specifying whether each element will be extracted or not. So it's a yes, no, so or true, false, I should say. So let's see how this works. Again, my vector is here, this series of numbers. If I type vec and then a vector of true, false, true, false, true, false, it simply means whenever there's a true in a given position, we'll return it. And if there's a false, don't return it. So hopefully you see how this works. Here, I have 5 elements in my vector, so I want the first one. The first one is 2, so it's returned. I don't want the second one, so this 5 is not returned. I do want the third one, which is 6. It is returned. I do want the fourth one, which is 8, which is returned, and I don't want the 10th. Okay, so the above shows that any index with true gets returned, obviously. Now, it is a somewhat contrived example because, well, we must specify every single true false. So it looks here that it's like it's an example more for illustration. In reality, it seems like it's a lot of work to specify each of the true false. This idea of logical masks is more useful in situations where in kind of one shot, you find something meaningful about your data. For example, let's say that you want to return all the values that are bigger than a certain number or equal to a certain number or smaller. Well, you can use this, and the syntax is actually quite efficient. So vec bigger than 5. This, in fact, based on what we've seen in the first week, will be a vector with true, false that evaluates this I suppose, logical condition for every element of the vector, right? So vec bigger than 5 will be a vector equal to, well, false, false, true, true, true. So if I have a vector here, false, false, true, 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 and then I take my vector again and I display false, false, true, 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 well, I'm going to get the last 3, because the last 3 are true, true, true. I'm going to get 6, 8, and 10. Hopefully that's clear enough. If it's not, just try this. Try this step by step in your RStudio. Okay, a few more functions that can be useful to extract elements from vectors. So the first one is which. So here I'm declaring a new vector to mix things up a bit. And I'm using the equality sign instead of the assignment operation. So as we saw in the week 1, that's valid. So here this command also creates a vector called x. And so how does which works? So it essentially it returns the position. Okay, here they're called indices of the elements of the vector that satisfy a certain logical condition. So which x equals 0 will simply return every element of the vector or the position of every element in the vector that satisfies being equal to 0. So here you see the third and the fourth are the only ones that are equal to 0. So which x equals 0 gives 3 and 4. And remember, as a logical condition, you need equal. If you try with only equal, not going to work. Which max simply gives you the index of the first occurrence of the maximum. Why first occurrence? Well, you could have ties for the maximum. So in this case, well, 9 is the largest element in this vector. It's present twice, but which max gives you 2 because 2 is the position of the first time the element is the maximum. Okay, it doesn't return 6, for example, because that would be the second index of the largest value. Which min, same thing, same logic. Okay, in this case, the minimum in this vector is -5. The first occurrence of -5 is position 5, so you get a 5 here. So maybe you want the last one is a bit of a trick. If you want specifically all values that satisfy a condition, or I should say the indices of all values that satisfy a certain condition, you can use which on the condition. For example, here, x equals min of x. That gives you many many positions, right? Sorry. Sorry, I lost my train of thoughts here for a second. So I was saying which x equals min simply will return all the positions of the numbers here that satisfy being equal to the minimum, right? So both the fifth and the seventh are minimums. So here you get 5 and 7. I don't know if it's worth it, but maybe let's go in RStudio in a second to explain the mechanic of which. In fact, this will be a sequence of true, false, and which will just give you the position of those true, false. So let's have a look at this. I'll just copy this in RStudio. So you see here, this will be a list of true, false. Because it's checking, okay, is all the elements of x equal to the minimum of x? Well, the minimum is obviously -5, so they will all be false except the fifth and the seventh. And then which of this means which of this is true, but specifically returns the positions of those true. So as I said, true is in position 5 and in position 7. So if I execute this, I get 5 and 7. Okay, extracting elements from vectors, an exercise for you so that you engage in active learning. So here, imagine that you have different vectors here. Now, later we're going to see that it would be convenient to organize this information into what we will call a data frame. But for now, they're just standalone vectors. But you should interpret them as giving you information about 5 different people, right? So the name of the people are there, Adam, Bob, etc. But and this would be the order of the heights of those 5 people, right? 165 centimeters and so on. And then you have their weight and you have their income. I hope it's an income in thousands of dollars. Well, even then, not amazing. Aside from Jinsha is doing quite well. If it's thousands of dollars. Okay, but anyway, for you, the exercise is what is the average height for people that are above 60 kilograms? So okay, let's see if you can find probably this idea of logical masks to solve this. So you want to, first you need to extract, well, who are those people who are above 60 kilograms? And then you need to compute, well, you need to find their heights, and then you need to compute their average. Average, I think we've seen already, you can compute that with the function mean. Okay, so hopefully you figure it out. But now we can see the solution. So, okay, here we've detailed it in a few steps. So we get a logical mask. So weight, again, weight is this vector here. Weight bigger than 60 will give you Okay, first one is not bigger than 16, right? This person is, again, I imagine those are kilos, but I suppose they can be any units that you have in your imagination. Second person is larger than 60, and so on. Okay, the third person as well. So now you have this vector of true, false, but you want the heights. Well, you want the heights corresponding to the truths of this vector. So the syntax we've seen before would be grab the heights, then square bracket. This is a vector of true, false, true, false. So, well, in this case, it's false, true, true, false, false. So it will return simply the heights that are in position 2 and 3, which are, of course, the people with the weight bigger than 60. So you will return the heights of the second and third person, which are here, 182, 178, Bob and Caitlin. And now you're almost done. Remember, you want the average of those points. Well, there's only 2 points, so obviously the average here will be 180. And this works by taking the mean of those 2 points. But now again, remember, those 2 points were obtained by this syntax. So overall, one shot, you have mean, height, weight bigger than 60, and you get this. And now this, maybe it's slightly confusing at first, but this is the kind of stuff you need to get comfortable doing in R, because with statistical analysis, there's all sorts of calculations you will want to do. Not exactly these calculations, but with this flavor, right? You find a subgroup of people, and for those people, you want to compute something interesting. Okay, what are the names of people with height smaller than 170? Okay, it's more or less the same type of question, but now we want to display simply their name. And you see, as a comment, the name is also a vector, but it's a vector of strings of characters. So it's a vector where the data type of elements in the vector is different. It is not a numeric data type. So let's see here. Same logic. Height smaller than whatever, 170 will give you a vector of true or false. And then from this, you can extract the actual name of all the people smaller than 170. Adam, Josephine, Jinsha. And then, okay, I suppose, okay, that's the same, that's the same answer, but in a different way. So, well, yeah, it's a similar solution. I mean, I think this is more efficient, this one, like fewer characters to type, but which height are smaller than 170, again, will be the same thing, like a vector of true, false, on the condition height smaller than 170. So you can use that as well. Yeah, it's going to work. I mean, it's going to give you, so it's not going to give you a vector of true, false. It's going to give you a vector of positions, like the numbers, basically. But then the syntax name, so Adam, Josephine, Jinsha, they are in position 1, 4, and 5. So in fact, this will be name 1, 4, 5. It's going to grab the elements 1, 4, 5 of name and return the same thing. So often in R, there's more than one way to do the same thing. And lastly, what are the names of people with a weight less than 66 and income above 70? Oh, so now there's 2 conditions. Well, same thing. You'll need to if you use logical masks, but you'll need the AND condition because you want 2 things. Maybe you can try to figure it out, or maybe you've figured it out already. So again, if we use the logical mask idea, we want we want here to be a series of true false that corresponds to 2 things. So you can use the ampersand, which is a AND operator that you can apply to vectors. So maybe it's worth it here to go in RStudio and show all the steps. So I'm just going to declare the same thing as on the slides. And then I'm going to copy paste this. Okay, so let's just execute this first. The weight smaller than 66. Well, I think I should probably I'm going to type this in my script first. Now from my script, I'm just going to execute some bits. So the weight smaller than 66, this will be a vector of true false. So all the people that have weight smaller than 66, which are only the first, fourth, and fifth. But now income bigger than 70, you see different people have income bigger than 70 than weight of 66. But this ampersand is AND, but that operates on vector element by element, compares the two vectors. So if you recall from well, last week's content, the whole thing will give you the positions of only the people that satisfy both condition. Weight smaller than 66 and income bigger than 70. So in this case, would be the first one, because true, true gives true. And then the second one is false, third one is false, then true, false is false, then last one is true, true. Okay, so the first and the last person satisfy both condition, and those are Adam and Jinsha. We get the same thing here, which is good news. Okay, now this was the vector. And again, the vector is just, like in mathematics, linear algebra, a one-dimensional series of elements. Usually numbers, to be honest, but it can, as we saw, can be, at least in R, and can be a series of characters. But now we get to other data structures. So other ways that R can organize information, and those are matrices. So view a matrix like you view a matrix in your maths classes, especially linear algebra. So a table. So now it has two dimensions, not only one. And also arrays. But arrays are basically you increase the number of dimensions. So a vector has one dimension, matrix has two dimensions, an array can have three dimensions, or four or five if you want to go crazy. But now let's start with matrices. Okay, this is what I said. Let me just finish this slide before we go to matrices. Important, like vectors, matrices and arrays can only store a single data type. So you could have a matrix of characters, but they will all be characters. Usually you'll have a matrix of number, but again, it's all going to be numeric. Okay, of course, that's a constraint, but usually, well, it's going to improve the efficiency of your coding over using something like data frames. We will see data frames in a few slides. Those are more flexible, so you can store information of different types, but they're less efficient. And usually in programming, you'll have this trade-off between you trade off some constraints, but for efficiency. If you want to have fewer constraints, then you have less efficiency. By efficiency, I mean usually actually the computing time is going to take, or maybe the amount of storage you need. Okay, all of this is better explained with examples. So let's start with matrices. So again, a matrix is really just like you see in your maths class, a table of numbers. So it has rows and columns. Now, the syntax here to create this specific matrix, we want a matrix with 4 rows and 3 columns. So the function is matrix. Then the first argument here is simply what populates the matrix. So in this case, we do something simple. We'll have all the numbers from 1 to 12. Remember, this notation is a vector 1 to 12. Well, it's a vector, but because we feed it to this function matrix, it will create a matrix, again, with 4 rows, 3 columns. And this argument here, by row, equals true, which means we will populate the matrix row by row. So those numbers, they will populate the first row, then the second, and then keep going. 7, 8, 9, 10, 11, 12. Now here, careful. Those things here, they are just the names of different columns and rows, right? So the first row has this symbol, and the first column has this symbol, but the actual values inside the matrix are these numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How to extract a specific value from a matrix is a similar notation as for the vector, but now you have 2 dimensions, so you need two indices. So now X is the name of my matrix, capital X. So capital X square brackets 2, 3 will extract the second row, well, the element in the second row and third column. So let's see, second row, third column, that should be 6. And indeed, the result is 6. Now here we create a matrix called Y. The only difference between this code and this code is, of course, the by row, which is now false. So if we populate the matrix not by row, it means we populate it by columns. And you see, of course, the result is different because now those numbers 1, 2, 3 up to 12, they populate the matrix filling the rows. So first we fill the first row, and then we keep going with the second and the third. And again, if we extract, in this example, the third, about the element on the third row. So the first index is for the row, third row, and 2. So for the second column, obviously we get 7. Okay, now we get to an array. So an array is a generalization of a matrix, if you will. Now let's start relatively simple with an array in 3 dimensions. So an array in 3 dimensions would mean, in essence, a collection of matrices. So a list of matrices, if you want. So let's see how this works. Z will be my array. Now I need 60 numbers in this case, so I'm not going to do anything fancy. I'm just going to have the numbers 1 to 60. Now, dimension here. So you see, here we have the rows and columns, but now because the dimensions are arbitrary, here I have 3 dimensions, but I could have 4, I could have 5. There's this argument called dimension. Okay. In the case of an array in 3 dimensions, what do these numbers mean? Well, again, an array would be a list of matrices. So this would still be the number of rows in each of these matrices. And this would be the number of columns. And the last one would be how many of these matrices do I want? So hopefully you see how this works. So that's the result. Now I have three tables. Well, yes, because that's an array. It's a list of 3 matrices. And so the first of these matrices is given here. Now, again, I'm populating this here by, okay, I populated by columns because the default argument here of by row would be false. So here you see the numbers 1 to 60 will fill the first matrix 1, 2, 3, 4, and then second column 5, blah, 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 up to the 5th column. Again, I have 5 columns because this argument is 5. And I have 4 rows because this argument here is 4. And then my second matrix in this array is here. We keep going because, again, we're going to populate those this array with 60 numbers. So after 20 comes 21 and so on. Okay, so hopefully you see. So and why can we do this? Well, it could be. In some applications, sometimes you have several matrices. You want to store them efficiently. So instead of creating an object like x1, x2, x3, blah, 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 so naming a different object for all your matrices, maybe it's more efficient to have a single object, an array that will store all your matrices. So all your, well, tables of numbers. I have occasionally used arrays in 3 dimensions. I've never used arrays in 4 or 5 dimensions. And now extracting the item, okay, so to extract from an array, well, same thing, but now again, you have 3 dimensions, so you have 3 indices here to place. What does Z2, 3, 2 mean? Well, extract the item in the second row and third column of the second matrix. So again, hopefully this works. Second row, third column of the second matrix, yes, it is the value 30. Okay, that's just a slide. How to interpret a 3-dimensional array? Well, that's what I explained. View it as a sequence of matrices. So you see, well, that's exactly like we had in this specific picture. Well, sorry, it's a bit blurry, but each of those things looks like a matrix 4 by 5, 4 rows, 5 columns. And in this specific example, you have 3 of them. So this exactly matches this example we had here. So a sequence of matrices. You could literally say that an array in 3 dimensions is a vector of matrices. A vector, what every element of the vector is a matrix itself. And then if you want to go crazy with this, you could say that a 4-dimensional array is a matrix whose elements are matrices, right? So a matrix, but every element in the matrix is a matrix itself, right? And then if you want to go in 5, 6 dimensions, maybe your head is going to explode and I don't know, you rage quit programming. But again, I've never used personally an array in more than 3 dimensions. So, but I'm not saying you never will. Who knows? Okay, this is, I suppose, repeating a bit of the same things, but let's make sure we understand how to extract from matrices. Okay, so this is just recreating my matrix. So here we showed you how to extract one element, right? If you want specifically the element in position, well, second row, third column, that's going to be a single number, 6. But you could extract entire rows or entire columns or more complicated things. For example, here we will extract everything that is on the first row and the fourth row. Now, comma means now we say what we want in terms of columns, where we only want the second column. So if everything that is in the second row and the fourth row and the second column will only be the number 2 and 11. So 2 and 11 here. Now, other example, again, I want first row, fourth column, and -2, remember -2, what this would do would be everything that is not the second column. So if, again, we want first row, fourth row, but not second column, all that remains is the elements 1, 10, 3, 12. And here, it actually returns a matrix. So careful here. 2 and 11, it's actually a vector. Well, yes, because, again, first row, fourth row, but only second column would be this and this. Well, that's all the elements in the second column, so it's actually a vector. But here, because you get element, this command asks you for 1, 3, 10, and 12, it's actually a matrix itself, because you have some elements in the first row and some elements in the second row. So put together, it stays a matrix. So the result here is another matrix. Okay, so we keep going with examples now. Again, first and fourth row, but now we don't want. Okay, that's a bit complicated syntax or nothing, because we don't want the second and the third column, but that's equivalent to having only the first column. So we're going to get the 1 and 10. 1 and 10. You can omit one of the indices entirely. So for example, x2, comma, nothing means I want the entire second row. So I want the entire second row. Well, yes, because again, first index is for the row. So I want the second row. And columns, I'm not specifying any columns, but not specifying anything means I want everything. So I want everything on the second row. I want all those numbers 4, 5, and 6. Okay, a pretty compact way to extract specifically one row or one column. I'm pretty sure you can guess how you would get a specific column. Okay, there's this slide here about recycling. It's important to recycle, but this slide is not about that. It's about a specific behavior of R. So given an operation on 2 vectors or matrices or arrays of different lengths, R will actually do something. It's actually going to complete the shortest data structure by repeating its elements. Okay, that sounds a bit abstract, but an example will clarify this. So if I have a vector here of those numbers and a vector that is smaller, right? Y is only 1, 2, 3, and X is those numbers. X plus Y will actually do something. And in fact, you might think this is a bit strange. You might have thought that this would create an error in R because you're trying to sum 2 vectors that have different lengths. So in mathematics, usually this is not allowed. But here, it works. R does something, but now you need to be a bit careful. Is that the thing you want it to do? I'm not sure. But what it's doing is recycling. So the X has 6 elements. If you add Y, it's fine for the first 3 because, of course, 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6. But now it wants to add something to 4. But of course, Y has nothing in position 4, but it's going to recycle the old values, and it's going to start again from the beginning it's going to complete y with another 1. So then it's going to add 4 to 1 and get 5. Then 5 adding something, well, it's going to recycle. Now we're up to recycling the value 2. So it's going to have 5 plus 2, 7, and you see the pattern, then 6 plus 3, then 9. And maybe that's a slightly strange behavior. Maybe it would be better if this gave you an error to make sure you're doing something legal. But anyway, that's the behavior of R for summing things or doing mathematical operations on things whose dimensions don't fit. Okay, another example is below. So we use the vector just 1 to 3 to fill a matrix with 12 spots. How is that possible? Again, recycling. So matrix, only 3 numbers here, and we want 3 rows, 3 columns and 4 rows. But recycling will mean that we start 1, 2, 3. Now we run out of values, but we start again, 1, 2, 3, and then we recycle again, 1, 2, 3, and then again, 1, 2, 3. Okay, sometimes you want to merge 2 matrices together. And for that, you can use either cbind or rbind. So cbind will bind 2 objects by columns. So let's first, okay. So in fact, you can bind vectors together, and then of course they're going to create a matrix because, well, 1 to 4 is the vector, it's not a matrix. 5 to 8 is a vector of 4 numbers, not a matrix. But if I say cbind, so column bind this and this, it will view the first as a column of 4 numbers and the other as a column, and then join them together. And voila, you get a matrix here of 2 columns, 4 rows, 2 columns. Now note, let me just show you in RStudio. You do need to use cbind to have this behavior. If you use only C, it's not going to create a matrix. It's just going to join 2 vectors together, and it's going to stay a vector, just a bigger one. I mean, it's simply this. If instead of cbind I just do C, it's gonna do something. It's just gonna, well, it's gonna bind 1, 4, 5 to 6, but it's gonna stay a single a single row of numbers, so a single vector. Okay, and again, once my B here has been created, it's a matrix. I can bind to it some other stuff. In this case, the number is 9 to 12, and then again, it's gonna add another column to this matrix. Can you guess what rbind does? Well, rbind stands for row bind. I think you see what it's gonna do. It's gonna bind together rows and create matrices like that. Well, I'm sure you're waiting for me to demonstrate what rbind will do. I mean, you should do it yourself, but let's see here. Rbind, I think you've guessed it, will create this. Okay, so instead of viewing this as a column, you want to join to another column, use it as a row that you will join to the other row, which is 5, 6, 7, 8. Now, you can perform all your usual favorite mathematical operations on matrices and vectors, but you do need to be careful about the syntax. So here we demonstrate this via examples. So I'm creating a matrix A that is 2 by 2 here, those numbers, a matrix B that is 2 by 2 as well. And here I'm going to create the diagonal matrix, or also called identity matrix of size 2 by 2. There's a specific R command for this. Diag2 simply creates this identity matrix. Recall, identity matrix as zeros everywhere except on the diagonal, and it needs to be a square matrix. A matrix with the same numbers of rows and columns. Now, again, A is here, B is here. A plus B, I think, does what you expect it to do, right? It's going to sum element by element the values in A and B. So 2 plus 1 gives me my 3 here. 3 plus 8 gives me my 11, and so on. But careful, A times B does not perform the usual matrix product that you have seen in your linear algebra courses. Rather, it's element by element multiplication. So what do I mean by element by element? Well, simply this. Again, A, the first element here is 2. it will just multiply it by the corresponding element in B. So 1, 2 times 1 will give me 2, of course. Then again, second element of the first row, so 3 times, where's my B here? 8. So 3 times 8 it will be 24, and so on. Like 5 times 2 will be 10. So this is not the matrix product. Okay, A divided by B, again, it's element by element. So 2 divided by 1 is 2. Sorry, it's 2 here, and then 3 divided by 8 is whatever this number is, and so on. Now, you can do matrix product, but there's a specific notation for this, which is percentage sign star percentage sign. Okay, so those three symbols in that order gives you the matrix product. I think you know that a matrix, well, a square matrix times an identity matrix of the same size will give you exactly the same result. It's not going to do anything to the matrix. So A times identity gives you the original A, 2, 3, 5, 4. More interesting maybe is the product of A times B, but again, a matrix product. So you get this result. Remember that what this means. So A times B in this fashion means, okay, so first row of A, but then vector product with the first column of B. So 2 times 1 plus 3 times 2, 8. We got the 8 here. Wonderful. Let's just do another one. 2 and 3. So first column times, first row times the second column of B. So 2 times 8 will be 16 plus 3 times 7, 21. So 16 plus 21, 37. We got a 37. So hooray, our matrix product works. So yes, you can enjoy the joy of linear algebra in R. Okay, T is just transpose. So T is a keyword, so it's a function. If you feed to T B, it will give you the transpose of B. What is the transpose? It's just that the first row becomes the first column, and the second row becomes the second column, and so on, right? So B, what is B's? Here, first row 1, 8 becomes the first column 1, 8. I think you know what the transpose is. Okay, there's just a comment here that diag has other uses, but I let you check that on the R help. Maybe I grabbed the opportunity to tell you question mark whatever function will open the help with the information about the specific function. So let me just show you question mark diag. Here, question mark diag will open the help. Sorry, the help. I always struggle with my H's at the beginning of words in English, but you see I have diag, so it's going to tell me, oh, I want to know about diag and more. So yeah, for example, you can use diag for other things, but yeah, I doubt you will use diag too much, but now you know it exists. Okay, more matrix operations. So you can actually solve linear algebra types of problems with the solve function. So solve AB can be used to solve AX equals B, where well, A is a matrix. Well, you're solving for X, right? And B can be a vector or a matrix, well, provided that the dimensions work. And so, well, let's just see how this works. Now, the other bullet point is that solve, if you use it alone on A, it will find the inverse of the matrix. So, well, if it exists, so remember, the inverse of a matrix is the matrix that when you multiply it by the original matrix, you get the identity matrix. So let's see how this works. Here I've declared my matrix 1, 2, 3, 4, and then I'm solving A and then 1, 1. But C1, 1 would be the vector of only two values, 1 and 1. So here I'm trying to solve A times something. I want to get to 1, 1. And here the solution is minus 0.5, 0.5. And we can check that it worked, because if I take the matrix product of A times my solution here that I called X, I get what I expect, which is 1, 1. So indeed, I have solved this equation, solving for X. And again, solve A gives me the inverse of matrix A, and the inverse is the matrix such that if you multiply it, again, using the matrix product by A, you get the identity matrix. So it seems like it's working. But careful that if the matrix is not invertible or inversible, I think it's invertible, you might get an error. I think maybe you can, I don't know if it's worth it, but since I've started talking about it, I'll go to RStudio to show you the simple example. So the matrix, if you fill a matrix with numbers, as we have done actually, so the matrix of like 1 to 9, that's actually not an invertible matrix, right? So A here, okay, it's not invertible. So if I type solve A, yeah, I get a mistake. System is exactly singular. So R picks up that it's not a, well, it's not capable to solve it because it's actually not an invertible matrix. Again, you would have seen in your linear algebra that not every matrix is born equal. Some of them are not invertible. Which actually causes problems sometimes when you try to fit some linear regression models, but that is a story for another day. Okay, the function apply. So function apply, you might not see straight away why it matters, but it's actually quite useful in specific context. So actually, you might see straight away why it's useful. So you apply a given function to all the elements, to the elements of all rows or all columns of a matrix. And so let's see how this works. Again, I'm creating a matrix here randomly. For some reason, I'm creating a matrix with the numbers 1, 2, 3, 4, and then 1 again, and then 6, 7, 8. Why not? To have 2 rows. So if I apply to this matrix the function median, but you see, specifying margin equals 1 means I apply the function to the elements of the rows. What does this do? Well, there's only 2 rows here. So the function here and here function, you can pretty much put any function that exists already that applies in this case to numerical value. So I could have put sum or median, or sorry, median is there, mean here for the other example, maximum or things like that. In R, I think it's not maximum, it's max, M-A-X. But anyway, I'm just finding the median in each row, basically is what I'm saying. So median, remember, is the number in the middle. If there's a even number, it's going to take the average of the 2 numbers in the middle, meaning the order of those numbers is 1, 1, 3, 7. So then the average of 1 and 3 would be 2, and that's the median of the numbers in this first row. Same thing was the median of the numbers. Well, they're already ordered, so the median of those numbers would be the number between 4 and 6, so 5. I think you know what a median is. Sorry if I'm insulting your intelligence. And then again, apply, you can apply it to the rows, to the columns of the same matrix. And by columns, I mean to all the elements of the matrix, but column by column. So again, if I'm finding the mean of all the elements in the first column, well, there's only 2 elements because there's 4 columns. Well, the mean of 1 and 2 is, of course, 1.5, and the mean of 3 and 4 and 3.5. And I think you see how this works. Now, this works in general. So again, you can have some fancy functions here that you plug, but there's some, I suppose, shortcuts. So those are, again, functions that are already implemented in R. So to find the sums of all rows, there's this row sum function. Again, the sums of the columns, it already exists, and the means of the rows exist as well, and the mean of the columns exists as well. So you don't need the apply function for those specific cases, is what I'm saying. I don't know if there's an example. I mean, let me just show you an example of how this works. For example, like in RStudio. Okay, so again, I'm declaring the same matrix that was just in the slides, and then row sums of the matrix. You see row sum, so there's two rows. It's computing the sum of those two rows. But again, I could have gotten the same thing by using apply, right? So apply, I apply to my matrix. I want the operation to be computed on the row, so I put margin equals 1, and my function, I put here it's sum, so it should do exactly the same thing. Yes, 12 and 20. Okay, given a matrix 3 by 3, well, that's an exercise for you. Use the apply function to create a vector called row sums. Okay, well, that's actually exactly what I just did. This video is starting to be pretty long, so I think I'll let you do this one. I don't think my explanations are going to add too much to the solutions that's already there. If you have any issues, you'll let me know. Okay, the last one maybe deserves a bit of explanation. So, well, the solution is here already, but verify with a relational operation that some rows equals some columns equals some x. Well, I suppose there's two things to say here. The first thing is just conceptual, like all those things give the same thing, because if you sum the total for the sums in all rows, or you sum the total, well, if you sum all the column sums, what you're doing, in fact, is just summing all the elements of the matrix. Hopefully it's clear. I mean, it's clear. And if we give an example here, like the sum of this column will be 3, and the sum of this one will be 7, the sum of this one will be 7, the sum of this one will be 15. But if you sum 3 plus 7 plus 7 plus 15, you've just summed all the elements of the matrix. Okay, so yes, conceptually, all those things should do the same thing. But then there's also something to say about the syntax. We're just checking two statements, right? Two true and false. So is the sum of the row sums the same as the sum of the column sums? Well, this should be true, again, conceptually. And now here we have a true. But now we also want to verify this is equal to sum. But sum x is not true false. So you do need to check, okay, is sum x also equal to sum row sums? And if this is true and this is true, you get a true. Maybe a bit confusing the syntax here, but it achieves what we want, which is to double check that this whole thing is true. This equals this also equals this. Okay, now just a bit of a global comment that maybe I could have said earlier, but it is here, so let's review it here. So far, the whole lecture was about what I call data structure. So we've seen vector, we've seen matrix, we've seen array. Do not confuse this with data type, and data type is what we covered in week 1. So data type such as an integer, a double, I mean, numeric is like the bigger category in which integer and double are contained, but then you also had logical, you had a character data type. So a type is, well, the type of information that you have, well, the data structure is how this information is put together, how this information is well, stored or structured. So for example, it's stored in a vector, in a matrix. We're going to see the data frame in a second. So you see that's a difference. And here, so if we want to check the type of information, we can use type of, that I think we've seen last time as well. Type of 2, that's a double. Type of hello, well, that's a character. Now, if we try this on a data structure, like a matrix, we will get the type that is inside the data structure, meaning type of, you see type of, that's a vector, but type of will simply tell us, okay, what's inside this vector? The elements of this vector are double. So individually, they're all double. And that makes sense because remember, the vector stores items of all the same type. So it makes sense that you only get one value. Okay, everything in this vector is a double. And again, okay, I create a matrix with high, and you see high is replicated everywhere. So okay, that's kind of an artificial example. But then I will get character again if I have type of this matrix. And again, why does this syntax work? It's again because of recycling, right? Matrix high will just recycle high everywhere. I can show in R here. So matrix high, I will get a matrix with high, 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 high. And I don't know if I said it 9 times, but I think so. But there's another function that you can use to find the structure, the data structure itself, rather than the data type. And this is the function class. So let's see. Class of the same high matrix, I get, well, here I don't know exactly why it gives me both, but it tells me it's a matrix, so it's an array. I think it's just because matrix is a special case of an array, and that's why you get the both. Honestly, I'm not too sure. But you see the difference, right? This tells you how the data is structured. It doesn't tell me the data type. And then, okay, we're gonna present data frame soon enough, but here I'm just creating a data frame, which is another data structure, and then class of my data frame I get data frame. Now, one slightly tricky thing, don't worry about it. It's probably not you were expecting. If I ask class of this, well, this I've been hammering about vectors since the beginning, so you would have expected maybe that this is going to tell you vector. And same thing here. Here I'm creating a vector with all my favorite courses. It's a vector of characters, which is totally fine. I might have expected that class will tell me vector. It doesn't. I don't have such a good explanation about it, aside to say that vector is actually kind of the fundamental structure. Maybe it's fair to say it's the default structure in R. So if something is not like a matrix or it's not a data frame, then it has to be a vector. I think because of that, class of this will actually tell you, okay, it's a vector of numeric type. It doesn't say vector, but by default, if it's not a matrix or a data frame or a list or any of the other, let's say, less basic data structures, is going to tell you, okay, it's a numeric vector. Well, it doesn't say vector here, but maybe you see what I mean. And here, it's not only a vector, it's a vector of characters. I think that explains why class gives you numeric here and character. But again, that's more of a side note. Okay, another data structure. So another way you can store information is the list. And you might think, okay, why do we need another data structure? We already have a lot, like vector and matrix and array that you can go in any dimensions you like. Well, careful. Remember, the big limiting factor with those data structures we've seen, they need to all be of the same type, the information stored in them. Lists, the big advantage is you don't have this constraint. So a list is a collection of objects in R, but each of those objects can have different data types. So let's just see a simple example. Okay, before we see the example of a list, there's just a comment here that, again, vector, matrices, arrays need to be of the same data type, the elements in them, I mean. So R will automatically convert them to the same type if they're not, and in fact, it's going to convert it specifically to characters. So for example, my vector 1, 2, those are numbers, but then the character A and then the logical value true, it's going to work, but it's going to give you something probably you don't want, which is all of them will be characters now. So you no longer can have mathematical operations on the elements of this vector. So again, type of vector, my vector is going to be character. So the solution to this is the list. So again, a list is a data structure. And if I create an object in R called myList, again, I use the assignment operation. List is the keyword I need, the function. What I feed to this function list can be objects of different types. So I'm going to create here a list with 4 elements, true. Then here, my matrix equals matrix, okay? What does this syntax mean? The object is this, the matrix, here is going to be a matrix of 2 by 2 with just the numbers 1, 2, 3, 4, but I'm giving it a name. So saying my matrix equals this, I'm giving a name to the second object in my list. which is allowed. And we'll see in a second why this can be useful. Okay, the third element is just a complex number. Sorry, it's a vector of complex numbers. So this is a complex number because it has the imaginary unit here, I. And the last one is a sentence, so it's a string of characters. Okay, now I've created my list here. Now I display it by just typing my list. Again, my list is just a name I gave it. And then you see that's how it displays. You might think, okay, it's slightly strange. I have like double bracket 1. Then I have dollar my matrix. So what is that? And then I have the matrix here. And then I have bracket 3. And then I have this vector of complex numbers. And then I have bracket 4, R is my friend. So this syntax basically refers to the fact we have a list. And so bracket 1, bracket is the first item in my list. But now by item, I mean it can be any object. So here, the first one is just the value true, but then the second is a whole matrix. You see, so that would be bracket 2. But it says dollar my matrix. Well, that's simply because I've named matrix a specific name, which can be handy sometimes. Actually, often. Okay, and this is just saying what I said. Left-hand side here, my matrix is a specific name I choose. So I want the second element of my list to be named my matrix. I'm very possessive. It's my matrix, you see? And that's the actual object. Now, let's say you have a list of objects. The notation to extract from this list is similar. There's a bit of a small twist. So to extract a single element, you actually need to use this double bracket thing. You see, double bracket 1 means the first element of the list. So if you want to extract it from the list, you use use double bracket whatever element you want. So for example, this command, my list bracket 3 bracket returns the third element of the list, and it returns it as itself. So for example, the third element was this vector of complex numbers. And by the way, not that it matters that much, but 3 is not a complex number, but because the first is a complex number, it transforms 3 to a complex numbers as well, meaning this syntax here, 3 plus 0i. But of course, mathematically, 3 plus 0i is just 3, right? But anyway, the point here, or the small twist, is just that you cannot use bracket to extract many elements, only one. So if you want a third specifically, that works. If you want to extract several items from the list, then you use the regular brackets. Then you use the regular one bracket. But careful, because you extract several elements from the list, the result will be another list. Well, yes, because you still have many of them. Like this is not a list because it's only one item from the list. But if I type my list, and again, only one bracket, 1, 2, well, this is the first 2 elements of my list, but there's still a list because there's still 2 of them. Okay, hopefully that makes sense. So again, the result of this is first element and then second element. Second element is also known by its name, my matrix. And lastly, because I named the second one, I can use this syntax, which is my list dollar my matrix. So my list dollar my matrix will also give me the result here. That would have been exactly the same, I believe, if I used my list 2 with the double brackets. I mean, let's just try. In real time, my list here, my list bracket 2 will give me my matrix here. Okay, I think that's enough about lists. Yes, aside the exercise for you, of course. Again, in the interest of time, maybe I'll let you review the solutions for yourself. I mean, let's not be lazy. Let's just review this. Length of my list. Well, yes. How many elements does my list have? 4. But just careful about what this 4 means. It means I have four things, but each of them contains other elements, possibly, right? This matrix, of course, contains itself four elements, but the four means I have this, and this. Do all elements have the same types? No. Obviously, you can see it straight away, but if you use here we use sapply instead of apply. So I think apply only works if you apply it to matrices, but I'm not 100% sure. Maybe I'll need to double check. But here, in any case, probably apply doesn't work to a list. Well, yes, because a list doesn't have rows and columns, so it wouldn't make sense for apply to work. So because of that, we apply the function sapply to the list, and what this does, it just finds a type of for everything inside the list. So logical, integer, complex character. Well, okay, we get my matrix here because we had named it. If you did not know this was a list, how would you find out? Well, use the function class we have just seen, right? Sorry, my voice is having some problems here. Too much teaching. But we'll power through. Class my list, I get list. Well, yes, it's a data structure, so I'm expecting class to return this. Does each element have its own name? Well, of course not. Only my matrix, because it was so special to me. Okay, here we are, data frames, another very important data structure in R. So data frame is what is used a lot for statistical analysis because many data sets have the structure or can be accommodated by what is in R specifically called a data frame. Now, in general, each row represents a single observation, maybe an individual, or it doesn't have to be. It can be a country and then you have several variables for that country or etc. I think you know what I mean, like a data set that I want to analyze. And then each column will represent a single variable. So if each row is a different country, maybe I have a column for GDP, a population, the population density, and so on. GDP per capita, life expectancy, and so on. And here so you might say, okay, if you have rows and columns, why don't you just use a matrix? Well, remember the matrix, everything in the matrix needs to be the same data type. So a data frame accommodates many different data types. So if a column is all just GDP, so maybe that's going to be like numeric, but another column could be something qualitative, like, okay, is it democracy or no, or maybe something like that. You see a qualitative variable, that would be a different column, again, in my example of the different countries. And so on. So yes, the data frame accommodates that different columns will have different data types. Okay, let's see a simple example. So I have I suppose similar example as before, but now I'm going to organize everything into a data frame. Easy to do. You just use the command data.frame and then bracket, and then this will be the first column of my data frame. So the gender of whatever those people here. So male, female, male, female. Then the height again, and then the weight, and then their names. And that's it. Now this data set is called BMI. Well, I suppose, okay, with their height and their weight, you can compute their BMI if you're into that. And this is how it displays. So you see, it looks like a matrix in the sense that it has rows and columns, but it's not the data structure is a new one called data frame, where again, every row is numbered here, first row, second row. And for every individual in this example, we have some variables about them. And you see, a bit like with the list, I've named every element. Well, every element. I've named every column, right? So the first column has named gender, the second column has named height, and so on. And again, you can use this dollar notation to extract a specific element. So BMI dollar gender will just give me all the elements in the. Well, you could call this a vector, I suppose, because it's a specific column of the data frame where all the types, the data types are the same. So BMI dollar gender, yes, you could say it's a vector with all those elements. And okay, I skipped this. STR, I think it's for structure, and it just gives you like a snapshot of what this data is. What is the structure of the data in this data frame called BMI? So here it is going to tell you have 4 observations of 4 variables. Gender is a character with those values, height with those values, and so on. If you have a huge data set, of course, it's not going to give you all the values, but you at least get some information about what you have in it. Okay, with data sets, often you want to merge 2 data sets. The situation is often that you have information about the same subjects in 2 data sets, but so some data sets are missing some variables and the other data set is missing other variables. So you want to combine them together to have all your information in one data set. So let's see an example of that. To do this, we're going to use the function merge. Now, be very careful what happens when not all subjects are present in both data sets, because again, conceptually, what you want is that, okay, I have everybody, in the case of individuals, everybody that's in the first data set, is also in the second data set. Then I merge it. But what happens if there's some missing people in the second data set, for example? Let's see. Okay, sorry. Again, I lost my train of thought for a bit. I'm creating a first data set here. Well, data frame to be specific, which again is a data structure in R. I call it just X. And so again, it has information about 4 people. Now there's an identifier for those 4 people. So, and here, I suppose this illustrates that the same people can have the same name. So sometimes the name is not enough to identify somebody. So here, for example, there's 2 James, but those James have a different ID, which then is fine, right? Everybody has a specific unique identifier. Then you have their height. Now in the second data frame, I have the same, yes, I have the same people. They're not in the same order. So you see, the first person is a James, but here the first person was a Mary. But we have the same ideas, ID, I should say. So we can recover who's who, basically. And see here, we have their heights in the first data set, but in the second, we have their weight, but we don't have their height. So you see the point, we want to merge those 2 to have all the information about those people in the same data set. This is what the first looks like. This is what the second looks like, where again, it's the same people. You see it's the person with ID 345, then 456 is in both, then 123 is in both, then 234 is in both, but in different order and with different variables. Now, you might think, okay, maybe we use cbind. It works in terms of like, it's not going to give you error, but here cbind doesn't really make sense because you're just going to join those 2 kind of, I don't know how to say, naively. You just put them together like this, boop. So you get this result, but which is weird because gender is duplicated, but you see they were not in the right order. So it doesn't really make sense that I have, Mary is here, and then I have James with other variables. So that's definitely not what I want. What I want is merge. And merge is actually quite smart. Just the syntax merge X, Y works. In the background, it seems to figure out that those subjects are the same because they have the same ID. And everybody that has ID 123 in the first data set is a female named Mary. And so that's fine, right? It's going to find, okay, from the first data set, the female ID 123 that is Mary and a height of 170 is going to find it in the second data set, okay? Female 123 Mary, but now there's a new variable, but that's fine. We're going to add it here, the 70. So now we have her height. Mary was 170 information in the first data set, and she's 70 kilos. I hope she's not 70 pounds. Information in the second data set that now is placed in the correct spot. Okay, so that all worked, and it's wonderful. What else? Yeah. So what happens if an individual is not present in both data sets? Well, they will be lost. So I think that's probably the behavior you want. That, okay, if somebody is not in both, they're just going to disappear. otherwise you wouldn't know how to complete the information, right? So let's just see an example of that. Now we create a new data set called Z. Some of the people there are the same as before, our James, our Olivia, our Mary. But the second James is not there, and now we have a new person, an intruder, Jennifer. Now Jennifer has ID 999 and also age 99, so what a coincidence. But you see, now if I merge X with Z, well, Jennifer is not in the first data set, so she's not here. And also one of the James, so which one? The James that is sorry, I don't know. We've lost the James, right? One of the Jameses, we've lost him. It doesn't matter. I mean, we can figure it out. Okay, the James with height 185 is still there. So it's the other James, right? So the James with the height of 180 is not in the Z data set. So we've lost him. And so we get those three. Now you could force the merge even for the observations or the individuals in this case that have incomplete data, right? That are in one data set but not the other. So you can force the merge, but then you're gonna get some NAs, which maybe is fine, but it depends on the specific task you have. Like, do you want, basically this keeps only the complete records, and this will keep, well, I suppose everybody, but then you're gonna get some NAs. So let's see. Well, yeah, careful. It's going to keep everybody, but you need to specify everybody. What's your priority? Do you want to keep everybody in the first data set or the second data set? So merge X, Z, all X true means everybody in the first data set will be kept. So again, our James that at a height of 180, we don't have his age because he's not in the Z data set. You see this where's my Z data set here? The second James is not there, so then we get NA. But if we say, okay, no, in fact, keep everybody in the second data set. So this would be all Y, T. And so in this case, we want to keep everybody in the Z data set. And then that's, well, that means we will have Jennifer. Okay, but of course, Jennifer is not in the first data set containing the height, so her height is NA. NA for non-available. But we can probably guess her height would be 199, probably. Okay. Let me just see what's okay. Now this slide is about factors. I want to tell you that factors exist now because they are quite useful in statistical analysis, but maybe it's not going to be so clear why we need factors for now. But I'll try quickly to explain, but then later we're going to encounter factors. So handling numeric variables is fairly standard in R, but for now we haven't really handled what is usually called a categorical variable. So a categorical variable, usually it means for different subjects, for different people, a variable that is not numeric, but that is a category that comes up quite often. Like there's a set number of those categories. For example, male or female. Okay, so here you would have two, at least in this data set, two categories for gender, male or female. So here conceptually, it's a categorical variable. And again, in my example of the countries, categorical variables might be, I'm not too sure, like, yeah, is it a democracy or not? Things like that, right? Name probably is usually not considered a categorical variable because it's like most likely you're going to get many different names, and it's not like you can organize them. Okay, it's not like really meaningful to put all the James together or all the Jennifers together usually, right? I mean, you could do it, I suppose, but now for such a categorical variable, we kind of need to tell R, okay, this is not just a random string of characters like a name would be. It's actually an important categorical variable, and for this we use the factor function, right? So okay, here we create a new variable, gender as factor, and we just say, okay, this gender thing is actually a factor. Okay, it's actually something that I have a set number of categories that I can then use to make some statistical analysis. For example, here I could analyze I don't know, the weight differences between male, female, for example. Okay, and then levels. So here, careful, I've created a new variable for my data. It's a factor of gender. And now I can display all the levels. Okay, and here again, there's 2. And again, okay, maybe it's a bit hard to grasp why this is useful just yet, but it will become apparent when we do more data manipulation and visualization. Because again, maybe in the visualization, I could display a chart of a certain statistic for male, a certain statistic for female, and then it would be useful to know, well, R will need to know that this is a factor. And then lastly, again, this is more of a side note, but for some R applications, you would need to know if a factor has a specific order to it. So for example, here, male, female, there's no natural order to it. You're not going to say female is bigger than male or the other way around, right? Yeah, I mean, unless maybe you're a misogynist or something like that, but let's not get into that, right? There's no natural ordering of male, female. However, something like a course grade, there is a natural ordering to it. And again, for some R applications, it could be that R needs to know that there's an ordering to those categories, basically, right? So, for example, here, grades. If I create the grades of my people as just this, a string, it's just going to be a string of characters. So declare like that, R doesn't know that it's a factor, doesn't know that it's a category. And here, sorry if I use the word factor and category interchangeably, it's just that in common language, in statistics, often we say categorical variable, but then R is this keyword factor to create a categorical variable. But anyway, grades as factor. So again, I can use factor like I did before here, but in addition, I specify all my levels, but I say it's ordered. So I say ordered true, which means here HD is bigger than D, D is bigger than C, and C is bigger than P, and P is bigger than F. So you see that's an example where, yes, there's a natural ordering of those categories. HD means it's higher, or it's better than D, and so on. And then lastly, if I output this grades as factor, you see it's going to tell me all of these things. What is the level of, what is their category or the level, right? And you have an NA here because something else, for some reason in this data, we don't know the grade of this person, so we wrote something else, but it's not one of those I've specified. So then it's an NA. And then it also tells you, okay, that's the ordering part, right? HD is bigger than D, is bigger than C, is bigger than P, is bigger than fail. But again, this bit maybe a bit abstract for now. Okay, a bit of a summary. In fact, it's a summary of, I think this is an exhaustive list of all the data structures in R. We have not covered all of them, but we've done quite a lot of ground. So vector, matrix, array, list, data frame, factor, we've all covered them. Dates, okay, so R can save objects as specifically dates, which probably we're going to deal with a bit later. And honestly, dates can sometimes be a pain. A bit like in Excel, for example, dates can be a pain. I don't think maybe R is better, but it can still be tricky. And time series, I'm not going to say anything about that. We're not going to deal about that here. Okay, this video is already very long, so I'll stop here. I'll make a separate video for importation and exportation, which is kind of a different topic, relatively short topic or shorter. But so for now, I'll say thank you very much. I'll see you in the next video.